The last thing that we're going to do is review the pH formulas that you learned from last year, and we'll do a few examples, just basic examples of using the formulas, and then ones where we're dealing with strong acids and bases. So this is your acid-base chemistry toolbox, I'll call it. It holds all of the key formulas that you need to be comfortable with. It's all based on this pH formula, right, and this relationship here from Kw. So they can all be derived from those two formulas. And if you need a review of that, you're welcome to come and see me. So pH is the negative log of the concentration of the H3O+ ions in the solution. Now it's important to note that chemists, although H3O+ is the more appropriate way to report this ion, if it's reported as H+, that's fine as well. So pH is the negative log of H3O+. Rearranging that formula, we get that the concentration of H3O+ is 10 to the negative pH. The P, recall, stands for the power. Okay, so in this case, the POH is the power of the hydroxide ion. So it's the negative log of the hydroxide ion in the solution. The hydroxide ion concentration is therefore 10 to the negative POH. The POH and the pH of a particular solution always add up to 14. Remember that no matter whether the solution's an acid or base, there is going to be some hydroxide and some hydrogen ions in the solution. And their pHs will add to 14. Their individual concentrations will always multiply to 1 times 10 to the negative 14. Let's look at a few examples here. The pH of rainwater collected in a certain region of the northeastern United States on a particular day was 4.82. What is the H+ ion concentration of the rainwater? Okay, if you look to the toolbox, we're looking for the hydrogen ion concentration. So the formula is simply 10 to the minus pH. So H+, and this is the case, you could write H3O+ or H+, both are accepted. And it's 10 to the minus pH, and it's equal to 1.5 times 10 to the negative 5. Okay, we have to remember to include our units of moles per liter. For significant digits, when you're dealing with pH, the number of significant digits in a pH is actually the number of decimal places. The 4 in here is actually just the placeholder. It's telling us what the power is. Okay, and then the other ones are actually the measured values. So in this case, there are 2 significant digits, so I reported 1.5 times 10 to the negative 5. In the second example, the hydroxide ion concentration of a blood sample is 2.5 times 10 to the negative 7. What is the pH of the blood? Okay. There are a few approaches you could take. You could use the Kw to find the H+ and then find the pH, or you could find the POH first by taking the negative log of the hydroxide concentration, okay, it being 6.60, and the pH is simply 14 minus that, which is 7.40. So in terms of significant digits, there are 2 significant digits in this number, so there are 2 decimal places in the POH. By subtraction, there are 2 decimal places in the pH. As a general rule, if you always keep 2 decimal places, you'll be fine with the POH. Now we're going to spend much of our time doing calculations in this unit of looking at pH of various solutions and looking at the pH after acids and bases have reacted with one another and examining titrations in great detail. What we can do at this stage with our knowledge from grade 11 and our basic use of the pH formulas is actually study solutions of strong acids and bases. Okay, because as you know, a strong acid or base is a substance where the reaction goes to completion. So there's no equilibrium. When you're dealing with an acid like HCl, which is a strong acid, it breaks up into H+ and Cl- completely. So if I know the concentration of my HCl, I'll know the concentration of my H+ in the solution, and I'll be able to determine the pH. Okay, the same is the case for bases that dissociate. With bases, we do need to be very careful of the stoichiometry and look at the formulas to help us with that. We'll see an example of momentarily. So in this first example, the concentration of an HNO3 solution is 0.0125. What is the pH of this solution? When you're dealing with problems in acid-base chemistry, you always want to first identify what type of solution you're using. So you need to identify this is a strong acid. Okay, because it's a strong acid, it dissociates completely. So that's the reaction, and we can see that in a 1-to-1 ratio, the concentration of the H plus is therefore 0.0125. Okay, there are essentially no HNO3 molecules in this solution. Now that I know the H plus, I can use my pH formula and take the negative log of the concentration, and I get a pH of 1.90. In the second example, it's asking for the pH of a sodium hydroxide solution. So first thing is to recognize that it's a strong base and know that it dissociates completely to produce sodium ions and hydroxide ions. Because of that, the concentration of the hydroxide in this solution is the same as the original concentration. They're in a 1-to-1 ratio. Now that I know the hydroxide ion concentration, I can find the pOH, which is 1.37. And then by taking that away from 14, I can find the pH of 12.63. In this third example, we've got barium hydroxide. Barium is a member of our big little B. So we know that this dissociates completely, so I get barium 2 plus. Okay? And in this case, I get 2 hydroxide ions. So although the concentration of the barium hydroxide is 0.0425, when it dissociates, the amount of hydroxide in the solution is actually double. So in this case, the concentration of the hydroxide ions is 0.085. Now that I know the concentration of the hydroxide, I can simply calculate the pOH and the pH, which is 12.93. So that completes our introductory review lesson of acid-base chemistry.